30 times. Ten times more. Two times more. Letting go and stop.
Okay, but if I'm born Caucasian with blue eyes,
yes,
that I won't be changing with epigenetics.
Not easily,
okay.
Not easily, okay? And so let's separate genes in two aspects. There's genes that make a physical body, so that's like the robotic, here it is, it's a machine, okay? But there are genes on how it's going to behave and how it's going to respond and what kind of issues it's going to face. Those are the changeable ones that we change from day to day, your behavior and the consequences of your behavior. Okay? It's not changing the genes, it's changing the readout. So the simple point is, a gene is a blueprint. Right away, this is the biggest problem in the world because the idea of a gene must be an illusion to a lot of people. There's something called a gene and it turns on and off. And it goes, no, let's clear this up. A body is made out of 100,000 different protein building blocks. It's sort of like a giant Lego kit. 100,000 different pieces. You can assemble the pieces this way, make a muscle cell, assemble them this way, make a brain cell. Different pieces, you can plug them together. The pieces are called proteins. They're very complex. The question is, where the heck do the proteins come from? And the answer is, the DNA is a blueprint to make a protein. This is where things get dicey after that for this reason. It's a blueprint. That's exactly what it is. And I say, why is it relevant? I say, well, you go into an architect's office and she's working on a blueprint. You lean over her shoulder and you say, excuse me, is your blueprint on or off? And she'd look at you and go, what, are you crazy? It's a blueprint. There's no on or off. Precisely. A gene is a blueprint. It has no ability to turn itself on or off. A gene doesn't know what the hell it does. And the idea is giving all this power to a blueprint has been an error all these years. It's not the blueprint that we're concerned about, it's the contractor who reads the blueprint. And I say, well, what in my biology is the contractor? I go, the mind.
Okay. Talk to me about your journey discovering this and your book, The Biology of Belief. As you said earlier, you were teaching these medical students one thing, and yet in your petri dish, you're finding out that other things are happening. How did you get this message out? How was it received? And now, you've taken it many levels further.
Yeah.
With your own consciousness.
It's only been about 30, 40 years since I recognized it, so I had a lot of opportunity to work on this. But the basic idea is simply this. Let's relate my laboratory experience to a human body so that we can connect it.
"30 times. 10 times more. Two times more. Letting go and stop.
A stem cell is an embryonic cell. We have billions of stem cells in our body right now. I don't care what age you are. The reason is very simple. Every one of us, every day, loses hundreds of billions of cells, normal attrition, normal death. I mean, just in the time we were talking, we probably lost 1 billion red cells in that time. And you got to replace 1 billion red cells. The lining of the digestive tract, 20 some feet of lining, the cells are replaced every 3 days. Well, that's, nearly 1 trillion cells. It's like, well, every day we're losing hundreds of billions. How many days in a row can you go if you don't replace? And the answer is not very far. So I say, we have stem cells, embryonic cells, that will replace them. So that's what a stem cell is. So I put a stem cell in a petri dish, it's an embryonic cell, and I make culture medium. And this is really important because we're going to talk about the connection. The culture medium is the equivalent of blood. If I grow human cells, I look at human blood, the composition, and try to make a version of it in a lab. If I grow mouse cells, I look at mouse blood and make a medium to grow mouse cells in. So I make the medium, and since I'm making it, I can change some of the composition. I'm synthesizing it. That's what I did. So here's the story, very simple. I put one stem cell in a petri dish by itself, and it divides every 10 or 12 hours. So first there's 1, then there's 2, 4, 8, 16, doubling. 1 week, 30,000 cells in the petri dish. But they're all genetically identical because they came from one parent. So I have 30,000 genetically identical cells. I split the cells into 3 petri dishes, so I have genetically identical cells in 3 dishes. But I changed the composition of the culture medium, a little chemistry change, in each of the dishes. So I have genetically identical cells, but slightly different culture medium. And in one set of dishes, the cells form muscle. In a second set, they form bone. In a third set, the cells form fat cells. You say, well, what controlled the fate? I say, they were all genetically identical. So it wasn't the genes, they all had the exact same genes. The only thing that was different was the environment.
Okay. So it's how those genes were expressed.
Right, but it was a reflection of the environment. So the cell is adjusting itself to the environment. Change the environment, it changes its adjustment.
Thirty times. Ten times more. 2 times more. Letting go and stop.
Okay, so you have this quantum leap in observation. You're like, whoa, what do your colleagues say in academia?
Well, they looked at me as a weird kind of guy, because everybody was into genes. Genes were that was before the Genome Project. That was the building up of our genetic repertoire of like everything's genes. And I'm the only guy out there in the corner going, it's not the genes. And they looked at me like the only guy out there in the corner and sort of dismissed it because it didn't fit their conventional story. Matter of fact, the first time I gave a lecture on it in front of my colleagues, I had left the university, but I'd come back because I needed a scientific audience to describe what I was working on. At the end of my talk, I said, thank you very much. And this room full of people, they just stared at me it was dead silent. I felt like really crazy. I was in front of the room. I said, thank you, and it just stared at me. And one guy in the back of the room, I remember he went twice. I mean, it was so clear. And when he did that, everybody looked at him. And then he just put his hands down in his lap. And then about a minute later, they all stood up and they walked out, all my colleagues. And I thought I was crazy.
Why does this happen? Why does that kind of thing happen? Because we think science is fact, but science is based on what's in vogue, right? And it's based on trends and all of that stuff, going back to Galileo or any of these things.
Every time a scientist has come up with a new idea, that scientist was always claimed as being weird or crazy or, way off track. And then those new ideas come in. Howard Temin.
Or sometimes they're just the weirdo.
Well, yeah, that's where you're going to have to distinguish. where does weirdo leave off and interesting person begin? Okay? And the fact was this. My research was repeatable every day, and you could predict it. The point about that is in science, prediction means you understand something. If you can predict it before you do it, then you have some insight. My predictions were always accurate. It just didn't fit the conventional storyline. And there was a choice, recant, you're a heretic, recant and just say, okay, I was wrong. And I said, no. Every time I was looking around, the results were coming in different ways from different places. So I held on to that. And it took about 20 years before science owned what I was talking about and gave it the name epigenetics. That's the new science.